In this section, we talk about phase diagrams. A phase diagram is simply a graphical way to summarize the conditions of different substances. So this right here is an example of a phase diagram. You have the three phases, solid, liquid, and gas, although you can have, some have multiple versions of solids, and I'll show you one of those too. And this doesn't have numbers on it, but if it did, it basically says that at whatever pressure this is, this would be the melting point, the point at which it goes from solid to liquid at this pressure. Okay, so given the pressures and I can dictate what the melting point is and what the boiling point is based on the different pressures. Okay, so this is for water, and so at 1 atmosphere we see that the boiling point is at 0 degrees Celsius. I'm sorry, the melting point is at 0 degrees Celsius. The boiling point is at 100 degrees Celsius. You also have something on here called a triple point, which is in green here, matching the green in the text. And it's the point on the phase diagram representing the temperature and pressure at which all three phases coexist. So I have at this point, which is 0.01 degrees C and 0.00603 atmospheres, all a solid, liquid, and gas coexist at the same time. Okay, this one only has one triple point. I'm going to show you another one that has two triple points. So this is a phase diagram for carbon dioxide is here. Okay, so this is the carbon dioxide here. Okay, and so at 1 atmosphere, we see at room temperature it's a gas. Room temperature would be somewhere out here. Okay, it has a triple point of minus 57 degrees and 5.1, and it still has the solid, liquid, and gas. Okay, so it's it's at 1 atmosphere, it undergoes sublimation at a minus 78 degrees. Sublimation meaning the solid to gas. It also goes from gas to solid at minus 78 degrees, which is, deposition at minus 78 degrees and 1 atmosphere. The bottom one here is, you see, a little bit different. First of all, it's got 3 triple points. It's got 4 regions. Okay, so it's sulfur, and sulfur exists as 2 different forms in the and 2 different crystal structures. Okay, and so this crystal structure, they call them allotropes in chapter 6. Okay, and this I call the throat lozenge or candy. Okay, it's one arrangement, and it also looks like needles. Okay, I believe that the rhombic is the one that looks like candy. The monoclinic is the one that looks like needles, but it's not important. What is important is the fact that there are 3 points here, or 3 triple points. So at this triple point, both the rhombic, the monoclinic, and the liquid exist. At this triple point, the monoclinic, liquid, and gas exist. And at this point, the monoclinic, rhombic, and gas also exist. So there's 3 different triple points, and so it's whatever 3 phases are touching at that point is what the 3 phases that exist at the same time. The critical point is the point at which a liquid state no longer exists. Okay, so in water, that's at 374 degrees Celsius and 218 atmospheres. That's right here. Okay. For carbon dioxide, it's 31 degrees Celsius and 73 atmospheres. This one's a fairly common one to take to supercritical because that's very doable conditions. You'll notice that this is orange, this is yellow, and this up here is kind of a mingling of those 2 colors here. The sulfur does not have a triple point there. Okay, I'm sorry, supercritical point. Okay, and so this again is the carbon dioxide. I'm sorry, this one's the water. This one's the water at 374 and 218. This one is another carbon dioxide at 31.1 and 73 atmospheres. So for a critical point, you have a temperature and a pressure, just like on the triple point, you have a temperature and a pressure. Okay. Now, carbon dioxide, this is again the phase diagram for that, okay? And so you can the reason I chose this one over the one that was in the textbook is you can kind of see the melding of the 2 colors up here. It's a range, but kind of continues out from this point to the edge of the graph. So this is what happens. It actually creates something called a supercritical fluid, okay? So, and that supercritical fluid has some properties that are like a liquid and some properties that are like a gas, but it's not either phase. so here it is. This is carbon dioxide at 20 degrees. And if you can imagine, this is like a test tube. It's just a sealed container. You very distinctly see the distinct levels between the liquid being here and the gas being here. Okay, this is just like looking at a glass of water. Okay, you see the water down here and you see air up here. At 30 degrees, because the critical point's at 31 degrees, at 30 degrees, okay, you see the fact that there's still a distinct gas phase up here. There's still a distinct liquid phase down here, but now the line between them has started to blur. Okay, there's no distinct line anymore about where it is. And at 31 degrees, so this is all at the 73, okay? Well, I take that back. They can't all be at 73 atmospheres because there's no pressure there. Never mind. But at 73 atmospheres and 31 degrees, this all changes to a combination of this yellow and orange. So it's a lighter orange, and the whole thing switches into that supercritical fluid state. Like I said, it's actually state. Now, for questions, the questions will be something like this. Okay? What phase is point A? So here's point A. Okay? And so it's kind of, this is all black, so it's kind of hard to see with all the dashed lines. So my phase diagram looks like this. I didn't quite follow it very well. There we go. That's my phase diagram. Those are the lines between my phases, I should say. So at A, this is a gas. At B, which is right here, oops, A is not a gas. A is a solid, and I could re-record this video, but I don't want to. B is a gas, and C is the liquid. What letter represents the triple point? So where's the triple point on this graph? And it's a little letter D. Which letter represents the critical point? And that is E. What would need to be to change the substance to a solid from its position Z? So starting out right here, how would I change it to a solid? And there's actually two correct answers here. Because I could go straight up, or I could go straight left, or any combination there. Okay, but basically they both involve lowering the temperature. So I could lower the temperature. And keep pressure constant. So that would be representative of this line here. Or I could, I'll go up here, keep pressure constant, I'm sorry, keep temperature constant. And raise the pressure. Or like I said, there's actually technically a third answer, which would be lower temperature. And raise pressure. Which would represent somewhere anywhere between these two arrows here. Okay? What would need to be done to substance to change it from a liquid from the previous question? So basically, it depends on which direction you decide to go here. But let's say, so if that's Z, let's say that this is X. Okay? So from X, it would be simply to, I could just raise the temperature and the pressure stay constant, but not by much. Okay, well, it would be from here, sorry. So I could raise temperature. And keep pressure constant. But if it was anywhere else, let's say that it was down here instead, let's make it V, okay? So from V, I would need to raise the temperature and pressure. Because from V, I would need to come up at least to here and then raise the temperature. Okay? All right, and that is the end of this section.